Okay, so we have built a fair amount of machinery with ordinary differential equations. We have seen how to apply some of this with vibrations in mechanical systems. Specifically, we looked at the case where there is no damping, the simplest harmonic oscillator problem, and then we looked at the damped harmonic oscillator problem, which gave us three different possibilities. So, namely the underdamped, uh, oscillatory solution, or the critically damped or over damped solutions where oscillations are not possible. And then we saw what happens if an external drive is present, right? So, the specific case of sinusoidal driving was instructive. So we saw that if you you know periodically push the system uh, for long times, it's really the external drive which is going to dominate the nature of the dynamics of the system. So the position of the system is going to in fact try and follow the external uh, force very, very closely for long times. For short times, of course, the solution from the homogeneous equation also matters, and this is what is called the transient part of the solution. And for long times, it's the particular solution which dominates, and this is called the steady state solution, because that's where the system eventually settles down to a steady state at long times. Now, so we saw that the nature of this solution is such that its frequency, the frequency of the position, is going to be the same as, it's going to have periodic motion and for long times, and this periodic motion has the same frequency as the frequency of the external drive, and there is a phase difference between the motion of the external drive and of the particle, and that phase difference is, we can work out tan phi in terms of the various parameters of the problem. So, but in this lecture we will see how one can what happens to your system when you drive it at certain special frequencies, right? So since we are subjecting your system to a drive in the lab, we have full control uh, over the amplitude or of the external drive. We have full control over the drive, the nature of the drive that we choose. So if we choose a cosine one, there are two parameters which we have the knob for in our hand. One is the amplitude and the other is the frequency, right? So the particular emphasis of this lecture will be to see that there's something very special happens if you drive your system at a special frequency which is known as the resonant frequency. And so the phenomenon of resonance has applications in all kinds of fields, but in our lecture here we will try and use the methods of differential equations that we have developed over many lectures to study resonance in this kind of a mechanical system in which vibrations are present and an external drive is introduced. Okay, so the differential equation of interest here is d squared x by dt squared plus 2b dx by dt plus omega squared x is equal to f times cosine of omega naught t, and we have seen that the solution, the particular solution, right, or the steady state solution for this problem is f divided by the square root of this stuff, this is the amplitude, times cosine of omega naught t minus phi. So the key point is that it's the same omega naught which appears as in the drive here, right? And then there is this expression for tan of phi which you can work out, right? So now the focus here is on this amplitude itself, right? So we have already seen that the frequency is just the same as the frequency of the external drive. So if you look at the amplitude, right, so let's study the square of the amplitude. So I'm going to call this fa of omega naught as f squared divided by f omega naught omega squared minus omega naught squared the whole square plus 4b squared omega naught squared. So if I study this quantity, the square of the amplitude, so then I see that there are two qualitatively different cases which come about. If I put omega equal to 1, b equal to 1 and f equal to 1, so now I see if I plot it, it's just a monotonically decreasing function as a function of omega naught, right? So it's like a featureless sort of decay with a function of omega naught. But on the other hand, if I choose omega to be 2, b to be 1 and f equal to 1, I get something more interesting. So look at this plot, and so now you see that there is an increase in this amplitude and there is a peak, right? So there is a special value of this omega naught at which the amplitude attains a peak, and then again if you keep on increasing omega naught beyond that point, it's going to decay, right? And for very large omega naught, so very large frequencies are it's as if like you're hardly doing anything to the system, right? So think of what omega naught going to infinity means. It means that you're shaking the system very, very rapidly. So when you have this very, very high frequency sort of drives, basically it does nothing to the system. There's no time for the system to get affected by it. So on the other hand, if you drive it too slowly, again the effect is not so optimal. But there is this very special in between frequency at which you can get very high amplitudes, right? So that's what is called resonance, right? Let's understand this. We can work this out analytically how this appears, right? So you take the derivative of this fa function and with respect to omega naught, and then if you put it equal to 0, then you see that it goes to 0 if omega squared minus omega naught squared, the whole thing times omega naught is equal to 2b squared omega naught. Now this is possible in two cases. One is if omega naught is 0, right? So omega naught is 0, you see this is actually an extremum point, and it's so here also. Well, it's not seen here, but it appears omega naught is 0 is an extremum point. But you can also have another second extremum point which appears when omega naught is equal to square root of omega squared at omega naught is equal to square root of omega squared minus 2b squared. So now some thought reveals why we didn't see a peak in the first case, right? So we had chosen omega to be too small here. It's only if your omega is greater than if omega is greater than square root of 2b, square root of 2 times b, only then will you get a real omega naught, which is for which you have an extremum point, and that's going to be a maximum in amplitude, right? So so the condition is that if omega must be, first of all, omega squared must be greater than 2b squared, and then omega naught, if you can choose your omega naught to be at square root of omega squared minus 2b squared, then you get a resonance, right? So this is this frequency square root of omega squared minus 2b squared is called the resonant frequency or the resonance frequency. And if you're driving your system at this frequency, it's called resonant driving, and it results in very high amplitudes, and this phenomenon is called a resonance, right? So recalling that the frequency of the corresponding free damped oscillation is, so suppose you did not have an external drive, right? So then we have seen how damped oscillation happens. If you remember, we called this something called beta, which is square root of omega squared minus b squared. So then we see that in fact the resonance frequency is less than this frequency beta, right? So if you're going to drive your system, if you want resonance, then for sure your system must be in underdamped regime, because if you're driving at resonance, you must have omega squared minus 2b squared must be greater than 0. So omega squared is greater than 2b squared, which in turn is greater than b squared. So omega squared is greater than b squared, which was the condition for driving your system for the underdamped oscillatory regime, right? So the point is that you are in the underdamped oscillatory regime, and then you're driving your system at this resonant frequency, then you can have resonance. So let's look at a plot of the amplitude function. Once again, we put f equal to 1 and omega equal to 1, and look at varying values of the parameter beta b, the damping coefficient. So if you look at this, so let's look at this a series of plots. So we see that if when b is very tiny, right, so then you get a big peak, and then there is this, as you keep on increasing b, the height of this peak shrinks, and there comes a value of D beyond which, there is no possibility of resonance. So in fact, it goes to a scenario where there is no peak anymore, right? So the key message from this plot is that as you keep on decreasing damping, there comes a point, right? So as you decrease damping, the magnitude of the peak itself keeps on increasing, and so when B goes to 0, in fact the damping becomes infinite, right? So you get this invalid solution Fa. If you put B equal to 0, then Fa of omega naught will just go to F by omega squared minus omega naught squared, which is basically infinity at omega naught equal to omega, right? So which is an invalid solution. It's a singularity. So in fact, this is the scenario of what is called undamped resonance, right? So there is no damping in your system and you're driving it at resonance. So this is a solution that we must go back and work this out afresh. Let's do it more carefully and afresh. So what we're doing is we're really solving this differential equation, d squared x by dt squared plus omega squared x is equal to f cosine of omega t, right? So on the right hand side, I've already put omega naught equal to omega, right? I'm driving my system at the same frequency as the natural frequency of the system, which is the condition of resonance, and there is no damping in the system. So this is a differential equation for which I should be able to work out a solution. So this kind of nonsensical infinity should not arise, right? So we will see how that can be resolved. So the key point is that you cannot take c sine omega t plus d cosine omega t, right, blindly as a particular solution, because in fact this is the complementary function, and that's where the error is. So when we were doing it earlier, we had taken this kind of a thing for the particular solution with omega naught, and now we are putting omega naught equal to omega, and then there is a difficulty because the particular solution becomes the complementary function is in fact the same. The two of them, when they become the same, in fact you have to get a linearly independent solution, and here you have to multiply by t, as we have seen. So we have to try out this form xp is equal to t times c sine omega t plus d cosine of omega t. Then if you differentiate once, then you get all these sines and cosines, and then there is a t times cosine. You have to collect all these terms carefully, and then you have to take a derivative again. So this will result in 2c omega minus dt omega squared times cosine omega t minus 2d omega plus ct omega squared times sine omega t. You should check this algebra, and then if we demand that this is a solution, this is a particular solution for this differential equation, we plug back this entire stuff into that original differential equation, and then we get these two conditions. So d will go to 0 and c is equal to f of 2 by omega. So if you choose your particular solution to be f over 2 omega times t times sine of omega t is a valid particular solution of this differential equation, as you can explicitly check. So the difficulty was we had not put in this factor of t. So this factor of t is absolutely vital here. So once you fix this, so then the full solution for this undamped resonance phenomenon is just a sine omega t plus cosine b cosine omega t. That's the standard complementary function, plus f over 2 omega times t times sine of omega t. So this t is absolutely crucial, and so this gives rise to an amplitude which keeps on increasing. It becomes larger and larger as time evolves. Let's plot this. So you see now so now you see that it's this t which is going to dominate entirely for large times, and it's going to become larger and larger and larger, and so in fact you'll reach a scenario where this system itself will break down beyond a point. It's unphysical for x to become actually arbitrarily large, right? But it can become very large, right? Can stay finite but extremely large, and then there's some kind of breakdown will happen to the system, and that's why resonance is a very powerful phenomenon which may be useful in certain contexts, but it may be extremely harmful in other contexts. So one harmful scenario of this is when soldiers who are marching on on a bridge are often advised to stay out of step, because if they were to march in step, they can be the external drive, and if their external driving frequency happens to match the natural frequency of the bridge, then this can lead to catastrophic consequences. But there are other contexts where resonance is something that is desirable, and efforts are made to drive the system at resonance. Right? Okay, so that's all for this lecture. We looked at resonance in here. Thank you.